Welcome to a screencast on equilibrium calculations. Okay, so let's take a look at an equilibrium calculation problem. And this one, we have a flask with hydrogen and bromine, each initially at a concentration of 0.50 molar at 700 Kelvin. And at equilibrium at the same temperature, the concentration of HBr is 0.80 molar. So the question is to calculate K sub C for the reaction below. And how we typically do equilibrium calculations is we set up a table starting with our initial concentrations. And in this case, we have an initial concentration of 0.50 molar for H2, 0.50 molar for Br2, and we initially don't have any HBr. No concentration was given for that because there isn't any initially. Now, the H2Br2 and HBr concentrations will all change as reaction proceeds until equilibrium is reached. And we don't actually know what the change is yet, but we do know HBr must be produced by this reaction. The reaction must go, quote unquote, to the right, because we start with no HBr, so the only thing it can do is be formed. And therefore, H2 and Br2 must be used up, they must react, and so the concentrations of H2 and Br2 will decrease, and the concentration of HBr will go up. Now, even though we don't know what the concentration changes are exactly, we can relate them to each other by using X to symbolize unknown change, and then noting that the H2 concentration goes down. The Br2 concentration also goes down, so we have a negative sign indicating decrease in concentration. And then the HBr concentration increases, and we put a factor of 2 in front of the X for HBr, because for every 1 H2, it reacts with 1 Br2 and produces 2 HBr. So the stoichiometry indicates a 1:1 to 2 stoichiometric relationship for the changes that occur. Now, if we know the initial and the change, we can get the concentrations at equilibrium. In this case, they're going to be in terms of X. We start with 0.50 molar H2. It goes down by X. So at equilibrium, we have 0.50 minus X. Br2 is the same thing. And HBr starts at 0, goes up by 2x. So it's 2x at equilibrium. Now note, the problem tells us that at equilibrium, the flask contains 0.80 molar HBr. So 2x is actually equal to 0.80 molar. Well, if 2x is 0.80 molar, then x must be 0.40 molar. And what this does is not only do we now have the concentration of HBr at equilibrium, but we can figure out the concentrations of H2 and Br2 at equilibrium. So HBr is 0.80 molar, and H2 is 0.50 minus X, which is 0.40, so H2 is 0.10 molar at equilibrium. Br2 is exactly the same thing, 0.50 minus 0.40 is 0.10, and so we now know the concentrations of each substance at equilibrium. And if we remember that the equilibrium constant expression, K sub C, is HBr squared, so the products or the substances on the right raised that concentration raised to the coefficient, in this case 2, and then divided by the product of the reactants or the substances on the left, and those are H2 as well as Br2, and each is to the first power because their coefficients are 1. So now it's just plug in values. 0.80 is HBr, and we square it. H2 is 0.10, Br2 is 0.10, and we do the calculation and find an equilibrium constant value of 64, and this is for the reaction above, at 700 Kelvin. So we would say K sub C is 64 for the H2 plus Br2 makes 2HBr reaction at 700 Kelvin. Now, the second problem is the dissociation of hydrogen sulfide into its elements, hydrogen and sulfur, when it's heated. And we are now dealing with pressures. We have a known initial pressure of H2S, and we are to determine the partial pressures of H2S, H2, and S2, all of the species involved in the equilibrium, at 1132 degrees Celsius. And note, we, in this case, are given an equilibrium constant value. K sub P is 0.0026 at the temperature we are dealing with. And as before, what we do is we set up our initial change and equilibrium, or what's sometimes called an ice table. And our initial pressure is 0.100 atmosphere for H2S, and we have no hydrogen or sulfur to begin with. Now, since we have some H2S and no H2 and no S2 initially, we know the reaction has to go to the right, making H2 and S2 and using up H2S. And we don't know how much it's going to react, how much change there will be, so we're going to symbolize that by X. And what we do know is if S2 changes by some amount, we'll call it X, and we know this is positive because S2 is being formed, then we know H2 is going to change by twice as much because it's 2-to-1 stoichiometry. And then we know that H2S will also be 2 times as much, but it's going to have a negative sign in front of it because its pressure is going to decrease as that substance reacts. Well, at equilibrium, so our next row is the equilibrium row, we're going to have 0 plus x is, of course, x, 0 plus 2x is 2x, and 0.1 minus 2x is 0.1 minus 2x. So those are the pressures of the respective substances or species when equilibrium is reached, and all of those are in terms of x. Now, how do we solve for x? Well, remember that we know the equilibrium constant expression. K sub P is the pressures of the products or substances on the right-hand side raised to the appropriate exponents, divided by the pressures of the reactants or the substances on the left-hand side raised to their appropriate exponents. So K sub P is pressure of H2 squared times pressure of S2 over pressure of H2S. And we'll now sort of tote up our where we got to in the last step. We knew the equilibrium pressures in terms of x. We know the form of the equilibrium constant K sub P, and that is in terms of pressures of each species. So we can substitute in our expressions in terms of x for the pressures into the equilibrium constant expression, and we get the following. Pressure of H2 is 2x, and that gets squared. Pressure of S2 is x, and that's to the first power. Pressure of H2S is 0.100 minus 2x, and that gets squared. And then remember that this equilibrium constant actually has a value. It's 0.0026. So what we have is an expression in terms of only one variable, x, that is solvable. Now, we'll talk more about how to solve these types of more complicated equations, but for now we're just going to say, okay, we do the math and we solve it, and we get our answer. In this case, it's x equals 0.015. Well, now that we know what x is, what the change is, we can determine what the pressures of each of these substances are at equilibrium. So S2 at equilibrium is equal to x. X is equal to 0.015. So the pressure of S2 at equilibrium is 0.015 atmospheres. 2x is the amount of pressure of H2 at equilibrium. So that's 2 times 0.015 or 0.030 atmospheres for H2 pressure. And then H2S is 0.1 minus 2x. And again, x is 0.015, so it's 0.1 minus 0.03, which is 0.07. So the pressure of H2S at equilibrium is 0.070 atmospheres. And then one last thing, it's often a good idea, if you have time, to do a quick check to make sure you solved things right. And if you did everything right, then the pressure of H2 squared times the pressure of S2 divided by the pressure of H2S at equilibrium, when we do that ratio with these values, we should get about 0.0026. Might vary just a little bit because of some round off types of uncertainty, but we should get about that value. And if we do that calculation, we check and we do in fact get the K sub P, and we know we did the math right and solved the problem correctly. And that's it for equilibrium calculations.